Welcome to AP Calculus 2.3b. In the first part of this lesson, we learned the power rule of differentiation, and we learned what the derivative of sine was, which is cosine, and that the derivative of cosine is negative sine, and we went through those derivations to see where we get that. At this part of the lesson, we're now going to apply those derivatives in order to find equations of tangent lines, which is, again, a major concept of the derivative is that the derivative is the slope of the line tangent at the point, and using the information from the derivative, we can find the equation of that tangent line. Just as a reminder, when we're finding equations of tangent lines, there's several key pieces of information that we'll need to determine. One is the slope of the tangent, and that is what is my slope, what is my m, and I find that slope from the derivative. That is my definition. One of my definitions of the derivative is that the derivative is the slope of the tangent line. But we're going to find this at some specific value of x, which we call a. We use x as a general placeholder and a to represent a specific value of x. Then I also need my point of tangency. What are my x and y values, or my x and f of x values? X and y, or x and f of x. And I'm going to find the x because I'm given that point. This is where we want to find the line tangent. But the f of x, I may be given the y value, but I may not. I may need to find that y value by plugging x into the function that I'm given. And then finally, we'll use the slope of the tangent and the point of the tangent, point of tangency, and plug that into the point slope formula. Y minus y1 equals m x minus x1. And finally, solve for y. Let's go ahead and start with our first example. Now, first of all, I can't take the derivative of this until I've multiplied it out and have it in polynomial form. So let's go ahead and work on getting this into polynomial form. I'm going to start by expanding this perfect square, so I'll bring the 2x minus 1 down directly. Then expand this square, x squared plus 2x plus 1. Then I need to distribute my 2x times x squared is 2x cubed. 2x times 2x is 4x squared. And 2x times 1 is 2x. Then I'll distribute my negative 1 minus x squared minus 2x and minus 1. I could take the derivative at this point, but I really rather combine my like terms first, simplify this, make it less work for me in the long run. Only 1x cubed form of x squared here and here for 3x squared. X terms here and here, these actually cancel out entirely, and one lone negative 1 left at the end. Now I can take the derivative because I have polynomial form. So f prime of x equals 2 times 3x squared is 6x squared, plus 3 times 2x is 6x. And the derivative of negative 1 is 0, so that is gone. So if my derivative function is 6x squared plus 6x, what is my slope of tangency? What is my slope at, they ask, at x equals negative 1? Well, that's going to be my derivative at negative 1. So I'll evaluate this derivative function for negative 1. At negative 1 squared is 1, and I get a slope of 0. So my slope of tangency, or my m, equals 0. Then I need to find my point of tangency. Point of tangency is x, f of x, Well, I know my x, it's given as -1, but I need to find that f of x. So I take my f of x function up here. And we can go ahead and leave this in its factored form. Might be a little bit easier to evaluate. And I'm going to evaluate this function for -1, f of -1. 2 times -1 minus 1, -1 plus 1 squared. This simplifies it a bit. -1 plus 1 is 0. 0 squared is 0. 0 times all of this is 0. So my y value, my f of -1, my f of x for that x is 0. With these two key pieces of information now, my slope of tangent and my point of tangency, I can use my point-slope form. Y minus y1 equals m times x minus x1. My x is -1. Well, y minus 0 is just y, and 0 times all of this is 0, so y equals 0 is my tangent line. In fact, it's the x-axis here at y equals 0. Let's try one with trig. I want to find, again, my instructions are the equation of the tangent line. To find the equation of the tangent line, I need to know the slope of my tangent. To find the slope of my tangent, I need to find my derivative. For this next one, we're going to work with trig. We're going to make one little change from your notes. Instead of finding at theta equals pi over 2, which gives us a pretty messy problem, we're actually going to evaluate this at theta equals 0. So to find the equation of my tangent line, I need to know my slope of tangency. And to find my slope of tangency, I'm going to need to find my derivative at theta, which is at 0. So I need to find my derivative. This is already in polynomial form. Here's a term and here's a term. So we'll find the derivative of theta equals, the derivative of sine is cosine. So I have 4 cosine theta. The derivative of theta is like the derivative of 1. So you can see the example here. 1 times theta to the 1 reduced by 1 gives me theta to the 0, which is just 1. So this is going to be minus 1. And then to find the derivative specifically at theta equals 0, it's going to be 4 times cosine 0 minus 1. And looking back at our unit circle, the cosine of 0 is 1. So 4 times 1 minus 1 will be 3. So the slope of my tangent line, or my derivative at 0, will be 3. Then I also need to find my point of tangency. That's going to be at theta, comma, f of theta. And I'm given theta up here as 0. And I need to find the function at 0 to find f of theta. So f of theta will be at 0 will be f of 0 equals 4. I go back to the function. This is my f of theta. 4 sine theta minus theta for theta equals 0. 4 sine 0 minus 0. And the sine of 0 is 0. So f of 0 equals 4 times 0 minus 0, which is just 0. So my point of tangency is 0, 0. That means its point of tangency is at the origin. And now I can use my point-slope form, y minus y1, right here, equals m, that's my slope of tangency, times x minus x1 y equals 3 times x. 3 times 0 is 0. So it's just y equals 3x for the equation of my tangent line. We're going to work another example with trig. There is an error in the worksheet. This theta here should not be there. We can just cross it out. Our actual g function is g of theta equals 2 plus 3 cosine theta. With that, again, to find the equation of the tangent line, we need to find our slope of tangent c, or the derivative at this point. And we need to find our point of tangent c. We'll start with the slope. To find the slope of the tangent line, I need to find the derivative, because the derivative is the slope of the tangent line. We'll go ahead and take the derivative. This is in polynomial form. G prime of theta equals the derivative of a constant is 0. And the derivative of cosine is negative sine theta. So I could rewrite this g prime equals negative 3 sine theta. To find this at pi, I'll evaluate for the point pi. Sine of pi is 0. Therefore, g prime of pi is 0. And the slope of tangent c is 0. Next, I need to find the point of tangent c. Well, the x point, or the theta point of tangent c, is given to me. It's pi. But the g point of tangent c, I'll find by evaluating my original function at theta equals pi. So that's going to give me 2 plus 3 cosine pi. Cosine of pi is negative 1. So we can evaluate this. 3 times negative 1. 2 plus negative 3 is negative 1. So my point of tangent c is pi, negative 1. Now we can write the slope-intercept form. Y minus y1 equals m times x minus x1. First thing we should do is simplify our signs here. This becomes y plus 1 equals 0 times x minus pi, and 0 times all of this is also 0. And to solve this for y equals negative 1. And we're done. Our final problem here does need to be put into polynomial form. I'm going to start by changing my radical into a fractional exponent. Then 3 on the x remains as the numerator. And this is an understood index of 2 because it's a square root. So I end up with x to the 3/2. And to put that in polynomial form, I will I'll divide top and bottom by x to the 3/2, which will give me 2x to the negative 1/2. This is now a polynomial form. I can take the derivative in order to start finding the slope of my tangent line. The derivative, when I bring this down, negative 1/2 times 2 is negative 1. X reduced by 1 is to the negative 3/2. And then I can rewrite this now into our radical form. Move my x back to the denominator. Negative 1 over x to the 3/2, or negative 1 over 3 is kept, and understood index of 2. This is my derivative, but what is my derivative when x equals 2? Now we can find the derivative of h, specifically when x equals 2. So that's going to be at negative 1 over the square root of 2 cubed. I get negative 1 over, I can take out 1, 2, I get 2 radical 2, and then I'm going to rationalize this and get negative radical 2 over 2 times 2 is 4. So this is my slope. Now I need to find my point of tangency. I'm given that x equals 2, and I need to find my h of x. It's going to be this function up here, evaluated where x equals 2. 2 times 2 over the square root of 2 cubed, or 4 over radical 8. Again, I can simplify. 4 over 2 radical 2, these cancel and give me 2. And then rationalize 2 radical 2 over 2, and simplify one more time. And I just get radical 2. That's my simplest form. So y is radical 2. Now I can find the equation of my tangent line, y minus y1 equals m negative radical 2 over 4 times x minus x1. Distribute that. Y minus 2 radical 2 equals negative radical 2 x, or x radical 2, over 4 plus 2 radical 2 over 4. Go ahead and reduce that to radical 2 over 2. And then I need to add that radical 2 to each side. And when I add that radical 2, I need it to be over 2, multiply top and bottom times 2. And get y equals negative x radical 2 over 4 plus 2 radical 2 plus radical 2 is 3 radical 2 over 2. And that's my final answer. Things just generally get a little bit uglier when we're dealing with radicals. And we'll move on to the next page. Our last page here deals primarily with the conceptual and the logical, which is vitally important for the AP Calculus exam. We're going to walk through each of these questions. Given the equation of a function, so if you're given some function f of x equals whatever, how would you determine the values at which the function has a horizontal tangent? Well, what does horizontal tangent mean? Let's draw a horizontal tangent. If I had a function and I were to draw a tangent that was horizontal, it would look like this. And what are the key characteristics? What are the key characteristics of this horizontal tangent? Well, it's a straight line, and it's horizontal. By being horizontal, it's parallel to the x-axis, we see here. And the slope, which given we're talking about derivatives and so forth might be important, the slope of this horizontal tangent equals 0. If the slope of a horizontal tangent is always 0, then that means the derivative of a function that has a horizontal tangent at that point, do another one here, that means that the slope of the function at that point, the slope of the line tangent to it, is also 0, which means that the derivative of the function equals 0 at that point. So if we needed to find where a function had a horizontal tangent, analytically it would be where their derivative of that function equals 0. Graphically, we can see that these horizontal tangents touch the function where it has maximums or minimums. So graphically, where f of x has a maximum or a minimum, relative maximum or relative minimum. So applying that information, in this question, where would this function have a horizontal tangent? And again, we said we have a horizontal tangent analytically where the derivative equals 0. Okay, so we're going to be dealing with the derivative. We want it to equal 0. Let's start by taking this function and finding the derivative, f prime of x. The derivative of this function is 3x squared plus 1. And I said that, and note that it asked at what values of x, or you might be asked where. These are referring to x values. So my goal will be to solve for x because I want to find my x value. And I'm told that I want my derivative, which I found here, to equal 0. So I'm going to set this equal to 0. And since I want to find values of x, I'm going to solve this portion right here for x. 3x squared equals negative 1. X squared equals negative 1/3. X equals the square root of negative 1/3. Well, I can't actually take the square root of negative 1/3. I can't take an even root of a negative number, so there is no x value where a horizontal tangent exists. Which means there's no horizontal tangent because f of x never equals 0 at any value of x. Because of that, f of x never has a horizontal tangent. Let's try this again. At what values of theta, it's functioning as my x, it's my independent value. At what values of theta would this function, f of theta equals theta plus sine theta, have a horizontal tangent? When I hear horizontal tangent, I should think derivative equals 0 or min or max on the interval from 0 to 2 pi. So I'm not going to consider 3 pi, 4 pi, or negative pi, or negative 2 pi. This is within the unit circle from 0 to 2 pi. So I'm going to start, if this is where my derivative equals 0, horizontal tangent, then I'm going to find my derivative. F prime of theta. Derivative of theta is 1. Derivative of sine is cosine. Okay, so I have my derivative, and then I want that to equal 0. Solving for theta, cosine theta equals negative 1. And I could use my calculator to find the inverse cosine. I can do this manually. I can look at my graph at my unit circle. And consider all of my values here. And at what point does cosine equal negative 1? By examination, I can see that cosine only equals negative 1 at pi. Now, I could also call that at negative pi, but we specifically asked for values between 0 and 2 pi. So the inverse cosine undoes the cosine here, theta equals, and the inverse cosine of negative 1 is pi. So at theta equals pi, my function has a horizontal tangent and also has may have either a minimum or a maximum. And that is it. We're finished.